Hi, my name's Richard Iliff. I'm from the Gold Standard Foundation. Welcome to this first module, acting as a tutorial on the methodology to estimate and verify ADALYs from cleaner household air. The first module provides an overview to the methodology. The specific areas that we will go through in this presentation are the eligibility criteria for applying the methodology, the approach used in the methodology, some specific requirements, and also recommendations for the application of the methodology. The main purpose of the ADALYs methodology is to be able to certify specific contributions against the Sustainable Development Goal number 3, which is ensuring healthy lives and promoting well-being for all at all ages. In terms of a background to this, the combustion of the typical fuels used for cooking, space heating and lighting in households results in a number of pollutants such as carbon monoxide, particulate matter, sulfur dioxide and nitrogen dioxide. Of these pollutants, the one most commonly and robustly associated with adverse health impacts is particulate matter. And more specifically, particulate matter of less than 2.5 microns in diameter, or PM2.5, is considered to be the dominant contributor to the disease burden from air pollution. Exposure to PM2.5 causes negative health impacts such as cardiovascular disease, respiratory disease, and lung cancer, all of which can result in premature death. Therefore, this methodology uses the exposure to fine particulate matter, PM2.5, as the best indicator of household pollution and adverse health impacts from household air pollution. In terms of the eligibility criteria for applying this methodology, any project that can lead to a verifiable reduction in PM2.5 exposure levels via a change in household energy use and/or emissions for cooking, heating and lighting may apply this methodology. Introducing cleaner cooking devices, fuels or practices are a common example. Cooking devices such as clean cook stoves using biomass, biogas, electricity, potentially even alcohol are applicable. Space and water heaters, heat retention cookers, solar cookers, and safe water supply and treatment technologies are all applicable under this methodology. In terms of cleaner fuels, electricity, piped natural gas, biogas, solar and alcohol are all applicable. In terms of practices, an improved application of eligible technologies such as the shift from solid fuel or kerosene to biogas are all acceptable under this methodology. The methodology may also include technologies such as solar lighting that leads to additional PM2.5 exposure reductions. There is an important nuance here in that solar lighting on its own is not eligible under the methodology. It must be coupled with another technology intervention, for example, clean cooking. Safe water supply and treatment technologies are only eligible if, prior to the project, in the baseline situation, solid fuels are being burned to treat the drinking water, for example, boiling by using wood fuel. Additional interventions are of course possible. The eligibility criteria reflect what is currently known of the potential benefits of various technologies and interventions. And if you have a project that you think will lead to a verifiable reduction in PM2.5, you're advised to check with the Gold Standard Secretariat to see if your technology can be eligible under this methodology. As a general rule, fossil fuels are not eligible under this methodology. Projects that involve a fuel switch to coal, charcoal, or kerosene are not eligible. Projects that lead to a greater efficiency in use of coal or kerosene are also not eligible. There are a couple of subtle exemptions. Projects that involve a more efficient use of charcoal as compared to the baseline or pre-project situation are eligible. And in the case of fossil fuels, use of modern fuels such as LPG or grid-derived electricity, these can substantially reduce PM2.5 exposure and are therefore eligible under this methodology. There are some specific eligibility criteria for clean cooking devices and heating stoves. The first of which is that the project stove must have a minimum of 20% thermal efficiency. And this thermal efficiency must be derived using a lab test using the latest version of the water boiling test or WBT protocol. Secondly, an incentive mechanism to discourage continued use of baseline technology must be included within the project. An example of this would be potentially a price discount for the project stove upon surrendering of the baseline stove. And in all cases, the incentive mechanism must be clearly described in the project documentation, and it must be monitored after the project has taken place. Finally, evaluation criteria to avoid double counting of the same project technology in other activities must also be included. For example, unique identification numbers, for example, stove serial numbers, retail invoice numbers, and cross-checking with other carbon offset ADALY projects or programs within the same project boundary must happen to ensure that the same device is not being credited twice. The approach within the methodology is the quantification of health benefits as a result of reduction in PM2.5 personal exposure due to the introduction of project technology and or practices. PM2.5 related health impacts are quantified using published exposure response relations that link PM2 levels to the incidence of 5 major diseases: stroke, ischemic heart disease, chronic obstructive pulmonary disease, COPD, lung cancer, and acute lower respiratory infection. Pneumonia is a typical presentation of this. And acute lower respiratory infection is also known as ALRI, and it primarily affects children. The methodology quantifies averted ADALYs, known as ADALYs, or dailies averted, and averted mortality, metrics used to quantify the health benefit of reduced PM2.5 exposure. A disability adjusted life year is a single metric that combines both mortality, which is the years of life lost, and morbidity, the years of life with disability. It's a common metric used by public health and development entities across the globe as a way of comparing the burden of disease due to various risk factors. The methodology has a two-step process. The first of which is field monitoring of PM2.5 personal exposure before and after the project technology is introduced. The second step, which is the conversion of PM2.5 exposures to disability adjusted life years, occurs within the HAPIT, or Household Air Pollution Intervention Tool. So essentially the exposure level before the project is fed into HAPIT, which then uses epidemiologically derived exposure response relationships to convert the exposure level into a number of disability adjusted life years. Using the two-step process of feeding PM2.5 exposures before the project and after the project, we're able to see the averted disability adjusted life years as a result of the project. HAPIT only functions if local measurements are available, and it does adjust its output according to national or subnational conditions where present. The study area within the methodology, known as the project boundary, is described as the physical geographical site of the baseline evaluation and of the project technologies. There are a couple of key definitions within the project boundary. In most cases, only members of the household, i.e. the family members living in the household permanently, targeted for the project technology may be included in the ADALYs calculation. The project boundary can also host the baseline and project fuel collection and production sites associated with fuel processing and transportation. An important exemption is that this methodology does not include community benefit from reduced exposures to people beyond the project target households. And the reason for this is because exposure levels at a community level are very difficult to monitor, and there's no clear relationship between them. Therefore, they are not included in this methodology. The pollutants included in this methodology: PM2.5 is the only pollutant addressed in this methodology. It is itself a mixture of components including black carbon, organic carbon, sulfates, and other trace chemicals. And evidence is currently inconclusive regarding the individual toxicity of these components on human health. However, existing relationships do exist between PM2.5 and public health impacts, and there are well-established exposure response functions for multiple health outcomes. Therefore, the PM2.5 exposure was chosen as the best indicator for calculating ADALYs in this methodology. Note that PM2.5 released during fuel production, processing and transportation is unlikely to affect household level PM2.5 exposure. The target population in this methodology are those identified for project technology distribution or sales. The target population could be within one single country or across multiple adjacent countries. This area, however it is described, provides an outer limit to the project boundary. The monitoring requirements, a brief overview. The aim of the project is to group the target population into representative scenarios. The first of which is termed a baseline scenario, which is the typical fuel consumption pattern, including PM2.5 exposure levels within the population before the project technology is introduced. On the flip side, the project scenario is the fuel consumption pattern, including PM2.5 exposures after the project technology has been introduced. There are discrete patterns that will influence the levels of PM2.5 exposure. For example, a baseline scenario 1 could be domestic threesome fire using wood fuel, and a baseline scenario 2 could be domestic traditional stoves using charcoal fuel. As different fuel types and different stoves are being used, you can expect very different PM2.5 exposure levels, and therefore they must be monitored separately to ensure an accurate result. Baseline and project studies are required as part of this methodology. An overview of the studies required at baseline level include identifying the baseline scenario, conducting a household survey, and then finally conducting personal exposure monitoring. In the project scenario, the key monitoring requirements are to conduct a household survey among project technology users, and then to conduct personal exposure monitoring on project technology users, and finally, to establish a usage rate by conducting technology usage monitoring. During these monitorings, any special circumstances in the household should be noted. For example, cooking or a festival or large parties or people eating away from home. The reason for this is because they will introduce a bias into the monitoring studies, whether it be a household survey or personal exposure monitoring. A requirement in this methodology is that baseline personal exposures needs to be reassessed. If a project lasts longer than 5 years, a new round of baseline surveys and coupled personal exposure monitoring needs to be conducted every 5 years. As you can see from the diagram, in year 0 of the project, the baseline personal exposure level is 400. In year 5 of the project, it's around 375. And in year 10 of the project, it's around 315. This reflects the fact that potentially baseline personal exposure levels of PM2.5 will reduce over time. And that's why this methodology requires the baseline to be updated every 5 years when the project reapplies for a new crediting period. The project personal exposure is monitored every 2 years or biennially until the end of the operational life of the project technology. ADALYs are estimated corresponding to the reduction in personal exposure level as a result of the project when compared to the baseline. The shaded area in the diagram represents the difference in personal exposure as a result of the project. So for example, you can see in year 2 with the red dot that personal exposure has been monitored in the project, and you can see that it's a figure of around 80. So the difference between 400 and 80, so 320, would be the difference in exposure as a result of the project. In terms of other monitoring requirements, carbon monoxide is required to be monitored in certain cases. Where carbon monoxide levels are observed at levels above World Health Organization air quality guidelines, these can result in adverse health effects. Therefore, projects involving charcoal-based interventions are also required to conduct carbon monoxide room area monitoring. This is because charcoal as a fuel tends to release carbon monoxide. If the 24-hour average carbon monoxide concentration exceeds the 7 micrograms per meter cubed World Health Organization guideline in a fraction of monitored households, that same fraction of project households from the total project population will no longer be eligible for claiming ADALYs. So for example, if 10% of households in the monitoring sample exceed the guideline, then 10% of ADALYs must be deducted from the monitored total. We have a number of recommendations for applying the methodology. At present, the monitoring requirements are relatively complex because very few people do them and there is little experience with it. This tends to mean that the monitoring studies are expensive. Therefore, there are certain cost-effectiveness issues that should be considered before deciding to apply this methodology. An incremental reduction in PM2.5 emissions will tend to produce a small number of ADALYs per household. This is because of the non-linear relationship of the exposure response curves for the 5 diseases in the HAPIT tool. So you can think of the curve as progressing as a plateau and then dipping very sharply at lower exposures of PM2.5. A technology that doesn't progress past the plateau area on the graph will therefore not result in a large positive health reduction impact. Likewise, low usage rates of the project technology will tend to produce a small number of ADALYs per household. This is because the benefit of the project technology will not be observed in the personal exposure monitoring studies. Low rates of displacement of the baseline technology will also result in a likely smaller number of ADALYs per household. This is because the emissions from the baseline technology will, on average, increase the levels of PM2.5 exposure in the household. Therefore, we recommend before applying this methodology that a pre-assessment is conducted, whereby usage, stacking, and durability of the project technology is assessed. Stacking refers to when baseline technology and other stoves are used at the same time as the project technology. It's also important to assess the acceptance of the project technology amongst the target population. This is to guard against low usage rates and low rates of displacement of the baseline technology. As a general rule, the project technology may be considered acceptable if it displaces at least 80% of the baseline technology use, and if less than 10% of households experience technology failure over the monitored period. We recommend that you check additional guidance and resources to come to your own conclusion before applying this methodology. For example, the study by Johnson et al., and you can refer to the Clean Cooking Catalogue on the link on the screen. Thank you very much for listening to Module 1. Look forward to welcoming you in Module 2.